Consider this problem where we're given an LTI system. The impulse response of this continuous time LTI system is as shown in this graph. It is a line from t equals -1 to t equals +1. And we can write the expression for this line. H of t equals, it's just a line of slope 1 and y-intercept 0. So it is h of t equals t from t equals -1 to t equals +1 and 0 outside that range. The input to the LTI system is x of t, and it is a pulse of height 2 from t equals -4 to t equals 4. And our goal is to find the output of the system, y of t, and it is given by the convolution between x and h, and that convolution is given by this integral. So the first step in evaluating this convolution integral is to replace all t's by taus. So that is what we're going to do first. Consider this figure where we have replaced all t's by taus. And step 2 is to apply time reversal to h of tau. We're not going to change x of tau. We're just going to apply time reversal to h of tau to obtain h of minus tau. That is the second step. Step 3 is we need to apply a time shift of t to h of minus tau. And again, we don't do anything to x of tau. We just apply a shift to the red function h of minus tau. Okay, so this is what we do, step 3. And the point that was initially at 0. So the center of the red function was initially at 0. And as we apply a shift, time shift of t to it, the point that was initially at 0 becomes t. And everything else will have that as reference. So the point that was initially at +1 becomes t plus 1. And the point that was initially at -1 becomes t minus 1 as we apply a shift of t. And the shift is represented by the variable t, and the possible values of t are all numbers from -infinity to +infinity, and we need to consider all possible values. And as we apply different amounts of shift to this red function, we'll see different types of interactions between the blue function and the red function. And that is why we need to split this total range of t to several ranges. And to understand what those different ranges are, we'll consider this graph again and try to draw graphs representing different amounts of shifts. So consider t equals -infinity and gradually increase t from -infinity to +infinity. If we were to draw a graph for t equals -infinity, our red function will be at tau equals -infinity. We wouldn't see it. We would just have the blue function. And as we gradually increase t, the red function would gradually move to the right. And up until this point, we haven't seen any overlap between the non-zero sections of the two functions. And that will be true until we get to this point. And this is reached when we apply a shift, or when t becomes equal to -5. So t equals -5 is an important point, and we put that on our list. T equals -5. This is the point when we start seeing partial overlap between the two functions. And if we further increase t, the overlap between the two functions will increase, and it will keep on increasing until this shift. Now this shift is -3. So we get to this graph when t equals -3. And that is also another important point. And we write it down in our list. And it's important because this is when full overlap between the two functions start happening. Further increasing t will continue that trend. We keep seeing full overlap until we get to this point, which is obtained by applying a shift of t equals 3. So t equals 3 is also another important point. After that point, if we increase t, we start seeing partial overlap between the two functions until this point where t equals 5. Beyond that, what we'll see is that the two functions do not overlap, and that will be true until t equals plus infinity. So we saw that in different ranges of t, the interactions between the two functions are different. So based on that, we marked some important boundary values for t, and we always add negative infinity and plus infinity to our list of boundaries. And based on these boundaries, we're going to split the total range of t to several intervals, several regions. Okay. The first region is from -infinity to -5. This is the region where we saw no overlap. Then from -5 to -3. So in this region, we saw partial overlap between the two functions. Then from -3 to +3, this is when full overlap happens. Region 4 is from when shift is between 3 and 5, and we saw that there is partial overlap between the two functions. And finally, from 5 to infinity, there is no overlap again. And so we already did the first two steps of convolution, replace t by tau, apply time reversal to h of tau, and now we are considering applying a shift of t to h of minus tau. The final two steps are multiply x and h and integrate. So we'll have to do the final two steps, multiply and integrate 5 different times because we have 5 different subintervals for t. So we'll consider one region at a time. So let's consider this one. Okay, and let's draw a graph that represents the first region. So this is when the shift is between negative infinity and -5. And in that case, no overlap happens between h and x. And when we say overlap, we're talking about just the non-zero parts of x and h. So if we take the product x of tau and h of t minus tau, from the graph, we can tell right away that this product is 0. And if we integrate something that is 0, we are integrating 0, so we get a 0. So in this section, in this region, when there is no overlap, the expression for y of t is simply 0. That is the first region. Now let's consider the second one. And let's draw a graph to show the two functions in this region as well. Now here we see partial overlap, so maybe something like this. And let's shade the overlapping region. So the overlap starts when at the left end of the blue function, so which is tau equals -4, and the overlap ends at the right end of the red function, which is tau equals t plus 1. So those 2 points are important because as we evaluate this convolution integral, so our limits, the integral range that we actually need to consider is only from -4 to t plus 1. So -4 is when the overlap begins. T plus 1 is when the overlap ends. Outside that range, the product between red and blue functions, the product is 0. So the integral is also going to be 0. So we just consider this part. So now we have modified the integral limits. Now we need to get the expression for x of tau and h of t minus tau. X of tau in the shaded overlapping region that we are considering, x of tau is just 2, and h of t minus tau, as we can see, is a line in the shaded segment. So originally we had the expression for h of t, which was simply t. Now we need an expression for h of t minus tau. It is going to be t minus tau. So we replace all t's by t minus tau to get h of t minus tau. So t minus tau d tau. Now we integrate with respect to tau. Okay, so we have 2 times t plus 1 plus 4 minus t plus 1 square. So we have t squared plus 1 plus 2t minus 16 divided by 2. So if we combine all the t squared terms, we get t squared by 2. If we combine all the t terms, we get 5t minus t. So we get plus 4t. And the constant term is plus 15 by 2. Let's write it as t squared plus 8t plus 15. So this is the expression for the convolution integral, and this expression is valid only when t is between -5 and -3. Now we have to find the expression for t in this range, -3 to +3. So let's draw a graph to show how the two functions look for this range of t. We'll see full overlap, so maybe somewhere here. And let's draw or shade the overlapping section. So what we can see now is that the overlap begins at the left end of the red function, which is t minus 1, and it ends at the right end of the red function, which is t plus 1. Those 2 points are important because they will become our integral limits. Right, because we're trying to integrate the product between x and h, and that product is non-zero only in the range t minus 1 to t plus 1, as we can see from our graph. Then we write the expression for x and h like we did before. X is still 2, h of t minus tau is still t minus tau d tau. So we get 2 t tau minus tau squared by 2 from t minus 1 to t plus 1. And with some algebra, we should get a 0 for this case. That was region 3. Now let's consider the fourth one. And we'll draw a graph to represent that case. And again, we'll shade the overlapping section. So now the overlap begins at this point, which is t minus 1, and it ends at this point, which is 4. So our integral limits this time are going to be t minus 1 and 4. X of tau is 2, h of t minus tau is t minus tau d tau. And again, we integrate with respect to tau. And this time, with some algebra, we should get negative t squared plus 8t minus 15. This is region 4. And the fifth one will draw a graph, and in this case, our the red function will be very much to the right of the blue pulse. So there is no overlap between the two functions, and in that case, we can say that y of t is going to be 0. So overall, what we are getting for our expression for y of t equals 0 in the first region, and in the second one, we had this. And then in the third region, we got a 0 again. And in the fourth region, we got negative t squared plus 8t minus 15, and then we got a 0 again. And so these 5 expressions are for 5 different regions. Let me copy those from here. Okay, so the first one is from negative infinity to negative 5. The second one is from negative 5 to negative 3. The third one is from negative 3 to plus 3. Then 3 to 5. Then 5 to infinity. So this is our expression for y of t. And what we're going to do next is sanity check to see if we made any errors. The first thing we can check is the range of the various functions. So the range of x of t is from -4 to +4. We're talking about the non-zero range of x of t. And h of t is from -1 to +1. So this means that for y of t, we should take the sum of these two, we get -5. We take the sum of these two, we get +5. So the non-zero range of y of t should be from -5 to +5. And if we look at our expression here, we see that it is from -5 to +5. So the range of y of t checks. The next thing that we're going to test is the boundary values. So what we see here is that t equals -5 is covered in both, included in both the first interval and the second interval. So if we evaluate t equals -5 using the second expression and the first expression, we should get the same number. If we evaluate y of t at t equals -5 using the first one, we get a 0. And using the second one, we would get 25 minus 40 plus 15, which is also 0. So y of t at -5 looks good. The next boundary value we're going to consider is for t equals -3. If we evaluate the third row at t equals -3, we get a 0. If we evaluate this at t equals -3, we're going to get 9 minus 24 plus 15, which is again a 0. So at t equals -3 also, the boundary values look good. The next one is for t equals 3. If we evaluate the fourth expression at t equals 3, we get -9 plus 24 minus 15, which is a 0. If we evaluate the third expression at t equals 3, it is also a 0. So we have a match again. Finally, at t equals 5, this expression yields -25 plus 40 minus 15, which is a 0. And this expression also yields 0. So the boundary values all look good. We didn't find any error. So that means this is our answer for y of t. So this is one way to solve the given convolution problem. So this is the graph we had in the beginning. And in some cases, it is easier to consider the other option. Since convolution is commutative, we could also have h of tau x of t minus tau d tau. So if we consider this integral, what we would effectively be doing is, instead of time reversing h and applying shift to h of minus tau, we would be doing that to x, and we would keep h of tau fixed. And there is a link in the description section of this video where I do it that way. And you'll see that the algebra is much simpler if you do it that way. So in general, it's a good idea to keep the function that looks more complicated, keep that one fixed, and the function that looks simpler, symmetric, like this, right? Try to time reverse and apply shift to that one. So in this case, if you time reverse and apply shift to x, so that means consider this integral. That would, the algebra would be much simpler in that case, which you can watch in that video, which in the description.